Okay. Yes, thank you, John, and thank you, Cody, for the invitation. What I'm going to talk about today is a set of mathematical formulae that characterize line bundle cohomology on spaces of interest in string theory. And apart from being interesting in themselves, I believe that there's a real promise for the way in which we do string model building in these results. And so this is the first and the main message. And the second message of the talk is that the mathematical structure of these formulae that characterize line bundle cohomology, they hide interesting surprises in them, and interesting surprises and information about the manifolds that otherwise would be difficult to infer. Okay, so yes. So what we all know is that string theory predicts that apart from the 4 dimensions that we see, there are extra dimensions whose topology and geometry is directly responsible for the physics that we observe. And everything that is an integer in the standard model of particle physics is supposed to be related to some topological quantity in the internal space. And everything that is not an integer, like masses and couplings, is supposed to be related to the geometry of the internal space. And this has to do with quantities like the Ricci flat metric on Calabi-Yau manifold, which are difficult to infer. So today I'm going to talk about the topology side of this story. And usually what one does is to pick the favorite geometry, internal geometry, and then derive from it the resulting physics. And this is the usual top-down approach, which is very expensive because there are very many options for what you can have as internal geometry. And it's just too much to compute, basically. So what one would ideally want is something in the opposite direction, to start with the physics that we all know, and then infer from it the topology. So in order to have that, you need formulae, which take you from topology down to physics, so explicit formulae, not algorithms. So in an algorithm, the information about the internal space is hidden, and you can't reverse this arrow. You can't produce a bottom-up approach. Okay, so where I come from is the E8 times E8 heterotic string, which is specified by 2 pieces of geometrical data. So that's a Calabi-Yau threefold and a holomorphic vector bundle over it. And the result of that is an n=1 supersymmetric theory in 4 dimensions, whose gauge group is given by the commutant of the structure group of V in E8. And the simplest class of vector bundles that satisfy these conditions, which ensure that you have n=1 supersymmetry in 4 dimensions, are line bundles. So line bundle sums in general. For example, if you take a sum of five line bundles, the resulting theory in 4 dimensions is an SU5 GAT. And then the multiplets, the SU5 multiplets, are in one-to-one correspondence with harmonic representatives of certain cohomology groups. So for instance, if you look at the 10 multiplet where the left-handed quark lives, you want to have three of these, excuse me, and you compute the number of 10 multiplets by computing the H1 line bundle valued cohomology on X. Okay, and similar for the other multiplets, SU5 multiplets. Okay, now the usual way in which one computes cohomology is you start with the space, so with the manifold and the bundle, and then you go to local data. So the usual motto is that cohomology is a global quantity. It tells you information about the global aspects of the manifold and the bundle from local data. So it infers global data from local data. So you start with the topological data of the manifold and the bundle, and then you go to local representation, to patches, or to a triangulation of the space, and then you bounce off back to global data. So what I'm trying to do is to operate at this level. So to ask the question, is there a direct arrow between topological data of X and V and other topological data of X and V, which are these cohomology groups? And the answer is yes, at least in the cases that we are interested in. Okay, so let me give an example which is very familiar of a topological formula. So if you compute the alternating sum of cohomology groups, which is the Euler characteristic of the bundle, then this can be expressed as an integral over the manifold of certain characteristic classes of V and X. And this is the Hirzebruch-Riemann-Roch theorem, or more generally, Ghiatia-Zinger index theorem. And it's a deep result in mathematics. It relates something on the right-hand side, which is topological, to something, this quantity in the middle, which is analytic. So the dimensions of these cohomology groups, they're really number of solutions to certain differential equations. So you compute, you know, something about a space of solutions to some difficult differential equations by just computing a topological quantity. So what I'm asking is there a similar formula for individual cohomologies, not only for the alternating sum, but for individual cohomologies? Okay, and yes, there are cases, there are nice bundles where you have that. For instance, if all higher cohomologies vanish, so if H1, H2, and so on vanish, then the zeroth cohomology is equal to the Euler characteristic. And you have an integral formula for it. As an example, take line bundles on complex projective spaces, and you have the Bott formula, the famous Bott formula, which tells you that you can compute the dimension of each cohomology group as a polynomial. So a piece of notation, if you're not familiar with this notation, so O of K is the line bundle on Pn, whose curvature 2 form is K multiples of the scalar form on Pn. Okay, so this notation will appear afterwards. Okay, so in the next section, I'm going to talk about some results on complex surfaces. So we looked at compact toric surfaces, we looked at generalized del Pezzo surfaces including and K3 surfaces. The general feature is that the Picard lattice splits into a number of regions, which are cones, and in each of these, the dimension of the zeroth cohomology group of L can be computed as the Euler characteristic either of L or of some other line bundle which is related to L, which can be obtained from L. So you have the Picard lattice, you have different regions, different cones, and in each of these, you have the zeroth cohomology given by some Euler characteristic. Okay. What we proved is that all the information that you need in order to obtain this formulae is the intersection form and the generators of the Moricone. Or alternatively, if you know the Moricone and the Neff cone, then you know everything. And in general, this may be difficult to obtain on arbitrary surfaces, this kind of information. But on surfaces such as toric surfaces, you can compute this information algorithmically. Okay, and so the intersection form and the Moricone, they give you both the regions and also the map between L and L twiddle, whose Euler characteristic gives the zeroth cohomology of L. So let me give an example, a toric example, and things will become a bit more clear. So I take one of the 16 toric surfaces, which corresponds to a reflexive polygon. And here is a picture of the Ron-Saveri group. So M1, M2, and M3 are the generators of the Moricone. Every line bundle that lives inside the Moricone has sections, has global sections, so has a non-trivial H0. Everything that is outside of that has vanishing H0. Now, the cone generated by N1, N2, and N3 is the Neff cone. Inside this, by Demazur's vanishing theorem, H naught is given by the Euler characteristic. So you already have a formula inside this cone. Now, what I'm saying is that there are 5 other regions, 1, 2, 3, 4, 5. So let me tell you how these regions are constructed. You construct them by taking the faces of the Neff cone and then extending in the direction which is perpendicular to that face. So for instance, if you take the face N2 and 3, there is one Morricone generator which is perpendicular to that, which is M1. So if you extend that face into the direction of M1, you obtain one region. If you take a face of codimension 2, which is, say, N2, so you have this edge, then you extend that in the directions which are perpendicular to N2, which is M1 and M3. And then you generate the brown region, and so on. So this is how the regions are obtained. And all that information is contained simply in the intersection form, or alternatively in the, if you know the Neff cone and the Morricone. Okay. So what are these regions really? They simply give you the information about the Zariski decomposition. So if you start with an effective line bundle, something that is inside the Morricone, you start with D, which is effective and integral, and then Zariski decomposition gives you a decomposition of D into 2 pieces. One which is Neff, this P, and then N. So N is effective and P is Neff. And P is Neff is on the boundary, actually, on the Neff cone. Is not inside the Neff cone, is on the boundary of the Neff cone. So you start somewhere inside this region, inside the brown region, and then you project onto N2. The result is a rational divisor in general. So it's a rational divisor class. It does not correspond to a line bundle. And then there is a rounding down or rounding up operation. And there is a theorem which tells you that the H naught of the original bundle is the same as the H naught of the round down or round up version of this P, of the positive part of D. So if you are lucky that the place where the round up and or round down version of P is a region covered by a vanishing theorem, then you're in business, because you can equate the H naught of the original bundle with the Euler characteristic of the bundle which you obtain through this operation. And you can do this in each region. So in each region, you project onto one surface. Then you take the rounding down and the rounding up, or rounding up. So in this way, you obtain these formulae. So I gave here just to show you how they look like. So in each region, H naught is equal to the Euler characteristic of some bundle. So this may look complicated, but it's really trivial. Everything is in terms of intersections of divisors, which can be computed explicitly. For instance, if you work in a basis, if you write D, so I have here D. If you write D in terms of the Morricone generators with coefficients K1, K2, and K3, then you can write the Euler characteristics explicitly in terms of these Ks. So this is a formula that tells you instantly what the zeroth cohomology is. Now on a surface, if you know the zeroth cohomology, you know everything. So you know H1 and H2 as well, because by Serre duality, H2 is dual to H naught, and then because of the index theorem, H naught minus H1 plus H2 is the Euler characteristic. So you have 2 relations and 3 quantities. If you know H naught on the whole Picard lattice, then you know the other 2 quantities. So there is a theorem, if you want to look in the paper, which gives you it gives you a formula for H naught on a toric surface, and there are similar results on generalized del Pezzo surfaces and on K3 surfaces. So more details are in this paper from September. So now, shall I stop for questions? Maybe I stop for questions later on. So in the next section, I'm talking about line bundles cohomology on Calabi-Yau threefolds, in particular on complete intersection Calabi-Yau threefolds. So we studied CC threefolds, we studied smooth quotients thereof by freely acting discrete symmetries, and some toric varieties and hypersurfaces therein. The empirical results showed that there are analytic formulae similar to what we've seen for surfaces for all cohomology groups. And because of their duality, is enough to understand the zeroth and the first cohomology. And then H2 and H3 follow automatically by duality. So far, we understood the zeroth cohomology. And what I'm going to discuss in this section is about the zeroth cohomology. Okay. The same pattern is observed that the Picard group splits into various cones, and in each of these, the zeroth cohomology can be computed as an index. You start with a Kähler cone of the manifold, and because of Kodaira's vanishing theorem, you know that in there H0 is equal to the Euler characteristic computed on X. So I put here the formula explicitly for the Euler characteristic. So L is because of the line bundle divisor correspondence. So L corresponds to a divisor class D. And then you compute the Euler number by computing the triple intersection number of D, take 1, 6, and then you dot D into the C2 of X. So in a basis, you have the triple intersection numbers Dij, and the C2, these coefficients. Okay, so you've seen this picture many times in the past probably. So this is the Kähler cone, this is a schematic drawing of the Kähler cone of a manifold. And what is known is that if the manifold admits flops, then neighboring the Kähler cone of X, there are other Kähler cones of the flopped manifolds, of the manifolds obtained by flop transitions from X. So on CCs, we didn't know that there are flops. But what we did was to use line bundle cohomology and to infer the existence of such flops. And also we were able to read some Gromov-Witten invariants from this story. So the empirical data is that if you look at the zeroth cohomology, you have various regions, various cones, and in each cone you can fit a polynomial formula for the cohomology. Okay, and what you do, so you see that there is a formula in the Kähler cone, you see that there is a formula in a neighboring cone. You fit the Euler characteristic formula to the zeroth cohomology data, and then you read off some intersection numbers and some C2. And what you notice is that the way in which the triple intersection numbers and the C2 computed in this region are related to those in the original Kähler cone, precisely in the way in which is prescribed by a flop transition. And what is known is that under a flop transition, the H0 does not change. So a flop, you have to think of a flop as a codimension 2 surgery operation. Is a process in which you have some P1 curves, some rational curves, which are taken out and replaced by other rational curves. But in codimension 2, it's an isomorphism, and line bundles correspond to divisors. So they correspond to codimension 1 objects. So because of that, there is an isomorphism between line bundles on X and line bundles on the flopped space. And moreover, the global sections, the number of global sections is not affected. So H0 of XL is the same as X and H0 X prime L prime. Okay, and now because you're in the Kähler cone of X prime, Kodaira vanishing theorem tells you that on that space, you can equate H0 with the Euler characteristic. So in this way, you obtain a formula for the H0 of the original bundle that you're interested in. Okay. So you read off the triple intersection numbers of X prime and the C2 of X prime from the cohomology data, and you see that this is they follow the pattern that is expected from a flop transition. And these formulae contain information about the Gromov-Witten invariants. Okay, so let me show you these formulae, the way in which the triple intersection numbers and the C2 change under the Gromov-Witten invariants in the corresponding curve class that you are, along which you do the flop. Okay, so I said most of this about the flop, about flop transitions. You have two manifolds and x prime. You have a singular manifold. You have contraction on one side and contraction on the other side. So some curves are being cut out and some curves are being replaced. Okay. Examples. I have three examples, three CC examples. The first one is a hypersurface in P1 times P3. D1 and D2 are generators of the Kähler cone. They are restrictions of the Kähler forms of the ambient space of the Kähler form data. So you compute cohomology algorithmically, and you obtain two cones. One is the Kähler cone of the manifold, and the other one is, and as I said, you obtain the triple intersection numbers and the C2 of the flop manifold. And what you notice is that if you go into a basis of divisors, which are the generators of the Kähler cone of x prime, the triple intersection numbers of x prime and the C2 become the same, are identical to those of x. And because of Wall's theorem, you know that x prime is the same, is isomorphic to x. So you have a flop between x and x prime, which is isomorphic to x. Okay, and the way in which D11 changes, so this going from 0 to minus 64, this 64 is indeed the Gromov-Witten invariant in the corresponding class. Okay, so what you notice if you look at the data is the same manifold here. You obtain that there is you notice that there is a symmetry, and this is exactly what I was saying earlier, that x and x prime are really the same manifold. So I wrote down the formulae. You have two Kähler cones, and then you have the wall separating the two Kähler cones, and then you have the two edges. And in each such region, you can write down a formula, a topological formula for cohomology. The second example, 7885, is different from the previous one. So it has a Kähler cone, it has another Kähler cone of a flop manifold, and has another cone. So what is this other cone? You look at it and you see that cohomology is constant if you go in a certain direction. So this direction corresponds to a rigid divisor. So the divisor that you have here is a rigid divisor class with Czersky decomposition in 2 dimensions. So there's a similar story here, that you can project a divisor from here onto the Neff cone, onto the Kähler cone, onto the green Kähler cone, and cohomology is invariant under that. So again, in each region, you can write down a topological formula. The third and last example, so 7863, is yet different in yet another way. So you have the original, the Kähler cone of the manifold, and then to the left and to the right, you have two cones. And these are, so this corresponds to flopped manifolds, which are again isomorphic to X, but both of them are isomorphic. So you have a Z2 symmetry relating the green cone to the blue cone. And then you have another Z2 symmetry relating the pink cone to the blue cone. Now these two Z2s do not commute with each other. And in fact, if you apply them one after another, you generate infinitely many cones. So apart from the green cone to the left, there are other tiny little cones, which you can't see because it's impossible to plot them, but it's infinitely many of them. And if you take the envelope of all that, you obtain the the boundary of the effective cone, which corresponds to a direction which is irrational. So this is quite interesting as a mathematical result. So this was the part about formulae, and let me say one slide about topological transitions in heterotic string. So I'm nearly running out of time. The question is like this. So if you have topological transition in the manifold, like a flop transition, what happens with the bundle? And in general, this is a difficult question, and it's an open problem. So topological transitions have been discussed in type 2 and in M theory, but in the heterotic context, it's difficult, and it's difficult precisely because of this. It's not known what the fate of the bundle is not known. So now, because we looked at cohomology and we looked at flop transitions, we have an idea of a proposal for carrying out the line bundle across a flop transition. And as I said previously, because divisors are not affected by flops, there is an identification of line bundles. So we know we can identify the line bundle on the other side of the flop. We can also compute cohomology. I said that the H0 is invariant, but the H1 is not. So the H1 changes, but it still can be found. And I didn't include that information on this slide. So what else you have to do? You have to check the anomaly cancellation condition. So you end up with a bundle, you end up with a heterotic model after the flop, and you want to see the fate of the anomaly cancellation condition. You want to see how the massless spectrum changes. And all this can be done. One point of caution is that sometimes you are not able to go to the flopping locus because of the conditions imposed on the bundle. So the bundle has to be slope stable, and it may not be possible to access the locus where you have the flop by keeping that condition. But if you go to, if you have enough scalar moduli, so if you go to manifolds on which you have enough scalar moduli, this is not a problem in general. So let me make a summary. So I put this one slide here with the work that has been done in this area, and there are people in Munich which studied similar problems, and people in Uppsala which have looked at these questions, and it's for you to look at later on if you're interested. So let me say a few words about what we are planning to do next. We looked at, in general, at manifolds with small Picard number, because these are easy to, it's easy to see by direct observation what happens, what the formulae are, and then to see something about the mathematical structure. But of course, for model building, sometimes you need manifolds with high Picard number. There is a question of how to do practically obtain formulae on manifolds with larger Picard number, and then machine learning is probably the key ingredient there. We already have built some tools for machine learning such formulae, and we are planning to apply them for higher Picard number manifolds. I talked about the zeroth cohomology. There is some structure visible in the higher cohomologies that is yet to be understood. Then is the question, so this is all about line bundles, but is there anything for non-abelian bundles? And we have hints that yes, there are similar formulae, or maybe not so similar, but there are formulae for monad bundles and for extension bundles. Then I talked about a bottom-up approach to model building at the beginning. It's still a question how to implement this. You have some formulae which relate the massless spectrum to the topology of the manifold and the bundle. How do you work this out practically? It's still a question. And then something that I haven't touched upon is the complex structure dependence of these cohomology formulae. So all the results that I presented lie space, but it is known that at certain loci in complex structure moduli space, there are jumping phenomena in cohomology. So can these be captured also by formulae? And this is very much related to the problem of moduli stabilization. So there is plenty of work to do, and I hope I sparked some interest in you with this presentation, and thank you very much for listening.
Great, Andrei. Thanks for the very nice talk. Do we have any questions? Cody does.
Yeah, Andrei, thanks for the very nice talk. You said you have an example where the effective cone is infinitely generated. Is that correct?
It's not infinitely generated. It's that it's got infinitely many subcones. So there are two generators. There are two generators, but within these bounds, there are infinitely many subcones. And each of these subcones corresponds to the Kähler cone of some minimal model of the original manifold. And I guess what we are talking about really is the pseudo-effective cone. So it's the closure of the effective cone, and it turns out to be irrational. So the lines are that they don't correspond to rational points if you compute the direction.
Got it. Okay, thanks.
Yeah.
Martin has a comment and a question.
Thank you very much, Andrei, for the very nice talk. So I wanted to make a brief comment on this very last point that you raised, namely towards this complex structure dependence.
Yes.
So there seems to be a classical story which is known as Fresnel theory, which tells you that on curves already,
yes,
there can be intricate phenomena as regard to these jumps. In fact, we had a recent result where we seem to find not topological formula for predicting these jumps, but let's say approximations for these. So that is the comment, and the question is,
this is interesting.
Regarding the geometries that you're looking at, where you find all these topological formulas. I'm wondering what the key property of these geometries is. So what is it that makes it possible to have topological formulae for the line formulas?
Yes. So thanks for the comment, and I'll be interested in the reference that you mentioned.
Sure.
Regarding the second question, so I think the question is how general these formulae are. Is there anything on any complex manifold like that? Can you write down something that, analogous to the Atiyah-Zinger index theorem? I have no idea, and it may be just that the manifolds that we care about in string theory are, in some sense, simple. They are homogeneous in some sense. Like we talk about projective spaces, we talk about toric spaces, we talk about embeddings in such spaces. It may be that there is an artifact of that you're able to capture the cohomology by a simple formula. But I don't know. I have no idea how far this can be pushed. So I'm interested to see examples where it fails, where it's not possible to write formulae, topological formulae for line bundle cohomology.
All right, we may want to connect on that. Thank you for the answer, Andrei.
Great. So in view of time, let us end questions there. Before we move on, let us all thank Andrei using our clap emoji for his very nice talk. And